Now, if we factorize here, we're going to get x plus 4 and x minus 3. On the bottom we'll get x, and then if we think about that one, that's x into x squared minus x minus 2. So that will be x minus 2, x plus 1. So let's just get rid of the working over here. Now, if we look at the top, y is equal to 0 when x is equal to negative 4 or 3. So that gives us x-intercepts. We can't have x equals 0 because of the bottom here, but we can see that we have vertical asymptotes. X equals 0, x equals 2, and x equals negative 1. Now, I'm not going to differentiate this. It's going to turn into a mess. I suspect there's no turning points anyway because of the degree of the top being less than the degree of the bottom, which has been the case in the previous examples. But even so, I think we could probably figure out turning points from the rest of our analysis anyway. Perhaps not precisely pinpoint them, but at least see if they're present. So let's look at different regions. So the functions that make up y are x plus 4, and I'm going to put them in order of when they change. So x plus 4 first, then x plus 1, then we have x, then x minus 2, and x minus 3. So that's in order of when they change. So the first one changes at negative 4. That's the value that makes this 0. To the left of it, it's going to be negative. To the right, it's going to be positive. Then we'll need to look at x being between negative 4 and negative 1. Then between negative 1 and 0. Then we're going to be between 0 and 2. So 0 and 2. And then between 2 and 3. And then x is more than 3. And of course the whole point of doing that is we want to know what happens to the overall function y. If our x value is less than negative 4, every single one of these is negative. And there's 5 of them, and that means that y is negative. Then this one changes sign, and the others are still negative, so overall it's still going to be positive. Then the first 2 have positive, and the rest are negative, so overall negative. And then the first 3 are positive, and then negative, negative. So overall that's positive. Then the first 4 are positive, and they're going to be negative overall, and then everything's positive. So overall it's going to be positive. And I always put these in this order here. So in order of when they turn negative, and then you get this nice cascade effect here. You don't have to think too much about making up the table. So we can probably do our sketch now. So let's put the sketch up here. So x-axis, y-axis. Now the y-axis itself, x equals 0, is one of our asymptotes. So let's put that along there. Let's label that as being x equals 0. And then we also have that x is equal to 2. So this one's x equals 2. And we also have x equals negative 1. Probably put that too far across, so let's just grab it and move it. In fact, I'm going to move this one a little bit. So let's just move that one a bit that way. Like so. So this one is x is negative 1. Now, y is 0 when x is negative 4. So negative 4 and 3. So it's going to be here as well. So we know those are x-intercepts. We know there wasn't a y-intercept. So what's going to happen? So, well, let's look over here first. So less than negative 4, we know overall it's negative. It's going to be below the axis here. And then between negative 4 and negative 1, it's going to be positive. So it's going to cut going this way. Now, negative 1 is an asymptote. So I think it's going to have to do something like this, where it comes through here, and then it's going to go off up here. What's going to happen over here, though? It's coming down below, and we know that the degree of the denominator is more than that of the numerator. So when x becomes very large, the bottom's going to be much bigger than the top, so it must go to 0. So there must be a turning point here somewhere, and then it's going to come back up towards the axis. Now let's look on this side. We know it's positive this side of 3. But the same sort of argument applies. When x gets very large, the denominator is going to be bigger than the numerator. It's going to tend to 0. So it's going to have to do something like that, where it has a maximum and then comes over and tends along the horizontal asymptote. Here, it's going to have to come this way. Between negative 1 and 0, the curve is always negative. But it must go out along those two asymptotes. The only way it can do this is to go down there, must have a maximum point in here somewhere, and then it must go down there. Between 0 and 2 it's positive, but it must go along the asymptote, so the same sort of argument applies. It must do that. But differentiating this thing here and finding when it's 0 is actually quite a long process without a CAS calculator. So you're probably not going to be expected, almost certainly not going to be expected, to find the actual turning points without the calculator available. And if you have the calculator available, of course you can produce the sketch anyway. So here we have an accurate plot, and we can see this minimum here, and we can see the maximum here. We can't really see features along here though, not on this scale. So I've produced a second plot, and we can see that it comes through this intercept and has the maximum. We can also see this one starting the curve back up towards the asymptote. So there'll be a local minimum somewhere in here. But that's the beauty of a sketch sometimes. We're able to show all of those features on a sketch. But with a plot, we might need more than one to see all of the features.